What specific problem does the VeriFree method aim to solve in the context of reasoning tasks compared to existing methods, such as R10 style training?
The VeriFree method aims to address the limitation of existing R10 style training, which relies on rule-based verification that is feasible only in specific domains like mathematics and coding. In contrast, VeriFree extends the training paradigm to general reasoning tasks where such rule-based verification is not possible. It eliminates the need for explicit verification by generating a reasoning trace and evaluating the likelihood of the reference answer conditioned on that trace, thus providing a reward signal without relying on a separate verifier model. This approach not only simplifies the training process, but also reduces computational overhead and variance in gradient estimation, leading to improved learning efficiency and performance across diverse reasoning tasks. Ultimately, VeriFree enhances the reasoning capabilities of large language models in broader contexts beyond those limited to verifiable domains.
How does the proposed VeriFree method work? Illustrate the algorithm step by step, including how the reasoning trace is generated and how the reward signal is derived.
The proposed VeriFree method operates by generating a reasoning trace and deriving a reward signal without relying on explicit verification. First, given a question, the model generates a reasoning trace denoted as Z and concatenates it with the reference answer from the dataset. Next, the likelihood of the reference answer y** is evaluated conditioned on both the question X and the generated reasoning trace Z. This likelihood serves as the reward signal for policy gradients on the reasoning trace and as a weighting term for supervised training of the reference answer. The algorithm effectively marginalizes out the answer, Y, allowing the model to optimize the reasoning trace based on the probability of generating the correct answer, thus enhancing reasoning capabilities while avoiding the need for a verifier.
Can you provide a simple example to illustrate how the VeriFree algorithm operates, specifically explaining the key components in the context of a reasoning task?
The VeriFree algorithm operates by generating a reasoning trace for a given question and then evaluating the likelihood of a reference answer based on that trace. For example, consider a reasoning task where the question is, what is 2 plus 2? The model first generates a reasoning trace, such as, first, I identify that 2 plus 2 equals 4. It then concatenates this reasoning trace with the reference answer, 4. The algorithm evaluates the likelihood of the reference answer 4, given the question and the reasoning trace, using this likelihood as a reward signal for optimizing the reasoning trace. This process eliminates the need for a verifier, as it directly assesses the quality of the reasoning by focusing on the probability of the correct answer, thus enhancing the model's reasoning capabilities without relying on explicit verification methods.
What are the theoretical and practical advantages of using the VeriFree method over traditional verifier-based reinforcement learning approaches?
Theoretical advantages of the VeriFree method include its ability to achieve lower variance in gradient estimation compared to traditional verifier-based approaches, as it analytically marginalizes out the answer, thus reducing randomness in sampling. This is supported by Theorem 1, which demonstrates that the VeriFree gradient estimator is more stable and informative, leading to better convergence during training. Practically, VeriFree eliminates the need for an additional verifier model, which reduces computational overhead and memory requirements, making it simpler and faster to implement. Empirical results show that VeriFree not only matches but often surpasses the performance of verifier-based methods across various benchmarks, indicating its effectiveness in enhancing reasoning capabilities without relying on explicit verification signals. Additionally, VeriFree demonstrates improved learning efficiency, achieving higher accuracy with fewer training steps, which is attributed to its continuous reward signals and the RLOO objective.
How was the efficacy of VeriFree validated in the study? Explain any experimental design, datasets used, and metrics employed to assess its performance.
The efficacy of VeriFree was validated through comprehensive benchmarking across multiple reasoning tasks, specifically using the MMLU Pro and Super GPQA benchmarks. The experimental design involved fine-tuning base models, Qwen3 with 1, 7b, 4b and 8b parameters directly using the VeriFree method, which was compared against a verifier-based approach, denoted as Verifier, and other baselines. The dataset utilized was curated from WebInstruct, resulting in approximately 61,000 samples, with a focus on high-quality data containing answers of fewer than 7 tokens. Performance metrics included average accuracy improvements, with VeriFree yielding gains ranging from 12% to 40% in accuracy on the MMLU Pro benchmark, and it was also assessed for response length and model confidence as proxies for reasoning capabilities. Additionally, the study highlighted that VeriFree achieved comparable or superior performance to instruct models and the verifier baseline without relying on explicit verification signals, demonstrating its effectiveness in enhancing general reasoning capabilities.
What notable results were achieved using VeriFree, and how do these outcomes compare to traditional verifier-based methods in terms of accuracy and learning efficiency?
VeriFree demonstrated substantial improvements in general reasoning capabilities, achieving accuracy gains ranging from 12% to 40% on benchmarks like MMLU Pro and Super GPQA when fine-tuning base models. Notably, VeriFree not only matched but often surpassed the performance of traditional verifier-based methods, such as the verifier baseline, without relying on explicit verification signals. Additionally, VeriFree exhibited better learning efficiency, achieving higher accuracy with fewer training steps compared to the verifier-based approach, attributed to its reduced gradient variance and continuous reward signals. This efficiency is further supported by the RLOO objective, which stabilizes learning and enhances generalization. Overall, VeriFree's results highlight its effectiveness in improving reasoning performance while simplifying the training process compared to traditional methods.